And welcome, friends. We are here for class number 2 this week, and this is the week prior to spring break. So next week, no class, and then following that, the Tuesday is also a holiday, so that's going to be off as well. So that means after lab this week on Friday, I won't see you back until the Wednesday, which I guess is April Fool's Day. So, maybe I'll see you back, or maybe I won't. Oh, so remember we do have lab on Friday. Lab is this gonna be? It's gonna be lab 8 on Friday. Okay, so we'll get going on that on Friday weekend. Actually, you'll have plenty of time to do this one, I suppose, but. Nonetheless, that looks like what we've got going. I did post up homework for yesterday, so hopefully that is good to go. And PLC 8, as usual, is for Friday, involving some PV graphs and I forget what else is on there, but it's all good stuff. So we left off talking about how heat affects substances, and water is a great example of what happens when you put heat into or take heat out of something. And I do want to mind my usage of the word heat here. It does sound like I am talking about heat as something that a material can store up. It doesn't really do that. As we know, heat is a transfer, and then it becomes the, say, thermal energy in the material, possibly the bond energy in the material. But the relationship of heat to the material that it's interacting with is much like having a force acting on an object. If I push something and then stop pushing it, right, and let it go, it doesn't keep my force, right? So the force is actually an interaction just happening while I'm pushing it. And it's the same with heat. If I put heat into something, it's not like the heat goes in and stays there. It goes in and becomes energy, right? So just like a force pushing something can become the object's momentum, and it does not hold the force with it. It is the same type of situation with heat, in the same way that I put heat into something or take heat. It's like I'm putting energy in or taking energy out. It just so happens doing it in the form of heat. So it's not something that's stored. So I should probably modify how I say things. But nonetheless, we were talking about what happens when heat goes into an object, and like water substance, and what happens when the substance is not at its phase change temperature. We talked about what happens when it is at its phase change temperature, and so we've come up with these two ideas that we have to have a thermal energy system where energy can go in order to cause the temperature to rise, and then we have the bond system energy, in which the substance, when at its phase change temperature, can have the energy, the heat going into that, causing the bond energy to change, and that changes the phase of the substance. So solid to liquid, liquid to gas, etc., etc. So we were in the middle of talking a little bit about how to set problems like this up, and so I left off with the situation here of 2 ice cubes into some water, and then the question of what is the final state of the ice water system. How has it come to equilibrium? What is the equilibrium state? Okay, so the idea is to find the equilibrium state. And I think we started off with 2 30-gram ice cubes. And we started off with 200 milliliters of water, of liquid. And I think we started at 25 centigrade, 200 mils of liquid water at 25 centigrade. The ice cubes we started off at minus 15 centigrade. which is a temperature that a lot of us would like to be able to access during the middle parts of the afternoon these days. Even just having a nice walk-in freezer would be kind of nice. You just head on in there during the hot part of the day, spend maybe a minute or so, and come back out. You'd be ready to go. All right, so I'm going to take my two 30-gram ice cubes right out of the freezer. I'm going to dump them into, this is, let's see, 12 ounces is 350 mils. So this is maybe more like 6 ounces or so. No, because that would be half. So it's maybe like 8 ounces. So 8 ounces of water. And this is going to be at near room temperature, although room temperature these days, outside probably hitting close to 30, I'm going to say maybe about 30, 32 degrees centigrade outside these hot days. I think yesterday was, yeah, upper 80s Fahrenheit, low 90s. So the question is, what happens when we put these ice cubes in? So just to kind of get an idea, okay, I've got my my nice room temperature beverage, and I would like to cool it off with a couple of ice cubes here. Once again, I am going to assume that heat is exchanged solely between these two objects. In other words, there's going to be some heat from the liquid going into the ice cubes, and I'm going to surround this with something such that I could say it was well insulated. Maybe I've got a lid over the top of it. I'm just going to ignore any type of exchange of heat with the atmosphere, okay? So heat only between these two, which means that the negative of the heat lost by the water, I'll use W for water and I'll use I for ice. Well, maybe I'll use IC for ice cubes. So this negative of that should equal the heat from the IC. I'll put IC like this, ice cubes. So it seems pretty straightforward, except that we don't know where we're going. So setting up the equilibrium for this, we can't, because we don't know what's going to happen. We're actually trying to find the equilibrium state. We do know that there's a latent heat and there's a specific heat, okay? So as the ice cubes are warming up, that's going to be a specific heat. When or if they start melting, that will be a latent heat, okay? So the question kind of comes in as to, well, what happens to these two substances? I have the liquid water at 25 centigrade, say up here, and I've got the ice cubes at minus 15, which is, say, down here. And the question is, how are they coming to equilibrium? So, for example, and I think maybe this was part of the PLC last week, or maybe it's this week. Well, I'm going to draw these. So this could, for example, cause the ice cubes to heat to 0 centigrade and then melt completely and then warm up again, like so, all the while cooling the water, right? So this is one possible situation. I have completely melted the ice. The ice has then warmed up. The liquid water, which was warm to start with, has cooled down, but has not changed phase at all. So that's one possibility. Another possibility would be a situation where this loses, right? It comes down to here, and then they go to there. And the ice, that would be silly. I don't want to draw right over the top of this, but like, or something like that. All right, I got to draw a whole another one. We got to draw another one. We got to do something whereby perhaps the water, the liquid, drops in temperature, freezes, And all the while, this ice is heating up, and they come to equilibrium there. In other words, they have frozen the entire 200 mils of water. Okay, that's also a possibility. Okay, they could also go to an equilibrium state in which the liquid has reached the 0 centigrade mark, the ice has reached the 0 centigrade mark, and they're going along at 0 centigrade, and the ice has kind of melted a little bit, but not all the way, and the water hasn't frozen at all. So there's possibilities here, right? So we're thinking through what's going to happen. We do know that when we have a sensible heat, we have M, C, and delta T, and when we have latent heat, we have M times L. Okay, so sensible and latent. Or if you like, specific. Okay, so the first thing to do, I think, in this case, is then to try and figure out how do we look at the step-by-step process here. So why don't we look to see what's possible? So what would be possible is the ice cubes are going to warm up to 0 centigrade. Okay, one question would be, how much heat would that take? We could calculate that. That would be a straightforward sensible heat calculation. So this would be ice cubes warming from minus 15 to 0. All right, so for example, how much heat does this take? And then we could compare that to, well, what happens if the liquid water went all the way down to 0? Okay, how much heat would they be giving up, right? If the liquid cooled all the way up. So then we can start comparing these two numbers and saying, oh, okay, look, these are equal, or this one's way bigger than that one, so this is going to happen, or something like that. Okay, so it's going to give us an ability to compare and get us on the track to seeing what we think the final state's going to look like. So let's start with the ice cubes warming from minus 15 to 0, and then we'll compare that. We're going to calculate the sensible heat of liquid water cooling all the way from 25 to 0. Okay, so we'll start here with this. As I've said before, the specific heats in these situations are usually assumed to be known, and it's kind of nice because ice has a specific heat which is basically almost half of the liquid, right? Liquid water, the C for liquid water would be 4.2 joules per gram per centigrade, whereas the C for ice would be 2.1 joules per gram per centigrade, which is kind of a nice thing to know. In this case, I want the ice cubes warming up. So this is Q for the ice cubes. I'm going to label that with an IC here. And I've got mass, I've got C for the ICs, and I've got the delta T. And what that's going to give me, I've got two 30-gram ice cubes, so we'll go 60 grams on this. I'm going to keep everything in grams because otherwise I'm just changing to kilograms, and I don't need to. I don't feel like I need to. C for ice, we already know it's 2.1 joules per gram per centigrade, and then the temperature change would be 0 as the final minus negative 15. So the temperature is rising by 15 degrees. This would be a plus 15 centigrade here. Right? Final minus initial for that, 0 minus negative 15. Okay, so if you calculate that, what's the easiest way to do that? I guess 15 times 3, 15 times 2 is 30, and then 30 times 60 is 1800, but then I got to add on a 0.1 here, which is going to give me a 1.5, 60, 90. So this is going to be 1800 plus 90. And I'm just going to check my units real quick to make sure I'm all good. My grams are going to go away, and my centigrades are going to go away. So I'm going to be left with joules here. And that's great because that's the unit of energy transfer. So I'm going to get, what did I say? 1800 plus a 90 for those two. Okay, so this is going to be 1890. So approximately 1900 joules. That's going to warm the ice cubes from minus 15 to 0. Let's now compare that. I mean, I have no idea what this, I don't know how big that number is. I don't really have a good feeling for how much heat is almost 2000 joules worth. I don't know. Let's compare it to how much we need to take out of the water to get the water from 25 centigrade all the way down to 0. So let's do that over here. All right. Liquid water cooling. Oops, not minus. It's going to be from positive 25 centigrade down to 0 centigrade. Okay, so how much heat is going to leave the water if that happens? All right, so once again, we're going to do Q as a sensible heat here, and it's going to be Q for water, so I'll put a W under here. Same idea. I'm going to have a mass of 200 milliliters, and I don't know if you are aware of stuff like this, so I will just let you know, because I'm about to do something, and you may not know why, but 200 milliliters, so in volume units, a milliliter is the same as a cubic centimeter. Okay, if I take those two volumes, they're exactly identical. And water's density is 1 gram per cubic centimeter. So in other words, it's 1 gram per milliliter. So 200 milliliters is 200 grams. When I look at the mass of this, I'm going to have 200 grams. I'm going to have the specific heat for water, which is joules per gram per centigrade. And then I'm going to go from 25 down to 0, which means my temperature is essentially, the change is negative. And that's going to be okay. I don't mind that because it's leaving, and I've got my minus signs already built into the energy balance here. I do want to know what the actual magnitude of the number is. So this is a little bit more interesting. I've got 200 times 25, so that's going to be 50. Oh, so you can see this is going to be a big number, right? I've got, look, if I've got this is 100. This is a little over 100, and then, so what is that? 0.2 is 1/5, so I would have to add 5. So this would be 105. 105 multiplying 200. So 100 times 200, well, that's 20,000. And I got to multiply the 5 times the 200, which is an extra 1,000. So 20,000. And what did I just say? 20,000 and 5 times 200, which is 1,000. So 21,000. Okay, so that's way bigger. That's a factor of 10 bigger than this. So I feel pretty certain that the ice has at least reached the melting point. Okay, this is, what did I just say? 21,000. All right, so this is 21,000 joules. All right, the negative simply means the heat left the water. Okay. All right, so we've got quite a bit to play with. Okay, we've got quite a lot. What's going to first happen is we can imagine that 1890 joules is going to leave the liquid and go into the ice, and it's going to warm the ice. So that definitely happens. The next situation is we need to examine ice melting. Okay, so once the temperature of the ice has hit 0 centigrade, it starts to melt, which means we're on that plateau with latent heat now. Okay, so when we go to latent heat, I need to think about how much energy is required to melt a particular, like a gram's worth. How much energy would I need to melt 60 grams worth of ice? All right, well, let's figure that out. Let's do that here. Actually, I'm going to do that over here. All right, to melt 60 grams of ice, I need to use Q ice equal to M times L. Okay, so this L number is one of those, just like the specific heats up here. We're going to assume this is a known, especially when it comes to water. For ice to liquid transition, the L value is 333 joules per gram. I don't know. It's just like these are easy numbers to remember for some reason. Like that one's half of that one, and this one's all a bunch of threes. I have no idea what the boiling one is. It's almost 10 times this or less, but it's about 7 or 8 times that number. So let's calculate 60 grams times this number here. Let's calculate 60 grams times 333 joules per gram. Oops, did I just barely fit that on the board? Oh, barely. Last parentheses missing. Okay. Well, okay, that's going to be a pretty big number, right? That's going to be 6 times, well, first of all, 6 times 300, right, is 18. 6 times 300 is 1800. And I've got 60 times 1800, 60 times 300, that would be 18,000. So this number is almost the size of this number, right? This number's big. So what's it going to be? It's going to be 6 times 300. So this is, I just have 18, 18, and 18. I got to add a bunch of 18s. Oh. All right. I've got 18,000 from that plus 1,800, which means I'm at 19,800 plus 180. What did I just say? 19,800, which is 19,980 joules. So that's to melt everything. That's to melt the entire thing. But you can see if that's so close to 20,000, and this is close to 2,000, that I'm probably above that number right now if I add these two together, right? If I take that number, that's about 20,000, I'm adding this, I'm above the 21,000 joules that the water can give up before nothing, right? Before nothing, because think about what's going on, right? The water is at 0 centigrade, the ice is at 0 centigrade. So it's not doing anything, it's not gonna freeze because there's nothing that's lower temperature to give heat to, right? So as long as the ice cubes reach 0 centigrade, and this is while the liquid is cooling, it hits 0 centigrade. Once it hits 0 centigrade, it's over. And so what this means to me is the ice cubes will melt, but not all the way. The liquid water will cool to 0 centigrade, but it will not freeze. Okay? So that's my analysis, just looking at the numbers. Hopefully that makes sense as to why. Let's take a quick look here. If I add the 1890 to this, this is approximately 20,000 minus 200. So if I take 20 off of that, it's 1870. So this is 21,870 to warm and melt the ice completely. So that doesn't happen, because I've only got this much from the water. Okay, so that 870 is extra, and that means that much is ice that has not melted. Let's figure out then the equilibrium state. So we know what the equilibrium state is. Let's figure out how much ice is left in the equilibrium state, because that's part of describing the equilibrium state. All right, let's do here. So Of the 21,000 joules that we had for the liquid to give up, we've used 1,890 of it. So that's 2,000 minus 110. So that's 2,019 plus 110. So we have right now, so let's just take it step by step, all right? We put the ice in, it starts warming up. So now now it's reached 0 centigrade. Okay, how much heat does the liquid have left to give up? So with the ice cubes now at 0 centigrade, okay, there's water heat is now 19, what did I say? It's 2,000 plus 110, so 1,910 joules left. Okay. Okay, so in other words, of the 21,000 that the liquid has to give up before reaching 0 centigrade, I've now used this much of it, and that means there's that much left over before the liquid hits 0 centigrade. So I'm going to take all of that because to completely melt the ice takes that much, which is more. Therefore, I'm going to figure out the mass of the leftover ice. And so I'm going to say that's going to be equal to Q divided by L, which is the 333 value. Okay. So when I do that, I'm going to get 19,110. Oh man, 19,110 divided by 333 joules per gram. Okay. Hopefully it makes sense why I'm doing this, right? This is, in other words, with that amount of heat, how much ice do I melt? Right? That's what this is asking. So I'm going to get a number here, which is going to say that's how much ice melted, and then all I got to do is subtract that number from 60, and I'll have the amount of ice that's left over. Okay. Dang. So, well, it's less than 60. I might have to resort to calculator on this one. It's 19,000 and there's 300 of those. So 19,110 and 333. Okay, I'm gonna not waste time on this one here. Let me call a friend. Okay.
It's 57.4.
Wonderful. Thank you. 57.4. So that's how much is melted. And therefore I should have 2.6 grams of ice left in 0 centigrade water. All right, so I would say that I feel like that statement describes the equilibrium final state reasonably well. I've got 2.6 grams of ice left over. It's at 0 centigrade, and it's in 200 mils of water, which is of liquid water, which is also now at 0 centigrade. And everything shuts off because the temperatures are equal, so there's no more heat transferring. All right, so I think that's the final state. I will put forth this mentality for problems like this. Typically, I am asking you to do all the math stuff, manipulations, algebra, whatever it is, do all of that, and then put numbers in. I kind of have to say, I want to not be burdened by having to do that. First of all, I wouldn't know how to do that because I don't know what the equilibrium state is. So I can't set up an energy balance right off the bat here. It's like you have to go find the numbers in order to figure out what's going to happen anyways. So in situations like this, don't hesitate to go put the numbers in right away and kind of do this type of process, right? And look at the, oh, I've got this much, I've got that much, I need this much, blah, 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 right? And I would also say that that's probably a good thing to do in general for these types of calorimetry problems. Other ones, I still want you to do the kind of the math stuff first. When it comes to these types of calorimetry problems, don't hesitate. The algebra probably is a waste of time, and it's never going to look good. So just pop the numbers through; it's easier. All right, so that's how to figure out a final state, and we've got a melting process in there. So okay, hopefully good times with that. Okay, let's do this. Let's take a little bit of time to talk about temperature, which I haven't really done explicitly yet. And we'll talk about some of the effects of temperature. Let's do this. All right. So in terms of temperature scales, I did mention this fairly early on in the situation here, when we started talking about the thermo stuff. If we just review the temperature scales quickly, just so that it's something that I can be sure that everybody has at least seen it once. The temperature scale, so there's essentially three temperature scales there's two temperature scales that we are interested in. There's three because we have to include the Fahrenheit one because that's our most common intuition here. And let's talk about their points. So in order to establish a temperature scale, you have to have a couple of points. And in history, the 2 points taken were those 2 points. So, well, that's not quite true. I guess Fahrenheit's not quite that way, but it's a little bit almost that way. So for the centigrade scale, these are fairly easy. The centigrade scale was basically completely set up for this type of situation. So the centigrade water freezing and water boiling, we hopefully pretty well familiar with that. A nice standard room temperature, like I think I may have mentioned, about 20 to 25 on the centigrade scale. Now, when it comes to the Fahrenheit scale, water freezing at 32 and boiling at 212 means there's 180 degrees between these two. So it's a slightly finer scale than this one, which is only 100 ticks between the freezing and boiling, whereas this has 180 ticks. So a room temperature of, say, 20 to 25 centigrade means that, you could be finer with it here. You could say, well, it's really between 68 and 72, and that's a much finer, you have the ability to make finer assessments on the temperature with these. Ultimately, Fahrenheit's 0 is where salt water freezes, because that was the coldest thing he could make, which is a very common thing in the Northeast, where you get ice on the roads and then you salt the roads and then the ice melts and then you can drive without having to skid all over the place. The problem happens when you get the ice and it's cold and then you salt the roads and it's still freezing. It's so cold that freezes. Okay, so once that freezes, you're screwed, because now what are you going to do? Now you've got iced salt water, and now you don't have any choice. You can't do anything. They did abandon the practice of salting the roads I don't know when they did this, but when I lived up in there, they were sanding the roads. They would put sand down instead of salt because I'm assuming that they have uh, awareness that runoff is not the greatest when you're just dumping thousands and thousands of saltwater gallons into, well, into the saltwater ocean, but maybe it messes stuff up. I don't know. Um, the other scale that we are mostly interested in is the Kelvin scale, which is the absolute temperature scale based on the centigrade scale. Okay, so this and this are quite well connected. It turns out that on the Kelvin scale, water freezing happens at 273 and water boiling happens at 373. So the way that you get from centigrades to kelvins is you just add the 273 and you're there. Okay. Now remember that when we were talking about the Kelvin scale, meaning the absolute scale, we related the motions of the particles that made up a gas and that subsequent kinetic energy to the temperature, saying that the temperature is kind of a measure of this random kinetic energy that's moving. And if it has zero kinetic energy, you can't do any better than that, right? There's no less than zero when you're talking kinetic energy. You either have kinetic energy or you don't have it. You don't have any negative. So the zero for Kelvin is where the kinetic energy of the molecules is assumed to be zero. And that means when I have the absolute zero, when I have the absolute zero, that's zero. And on the centigrade scale, that would be minus 273 centigrade. I think on the Fahrenheit scale, that turns out to be around minus 470 Fahrenheit. So it's chilly. Okay. There is one other temperature scale called the Rankine scale, which is basically like the Kelvin scale is for the centigrades. It's basically the absolute scale for the Fahrenheit system. It's called the Rankine. And so it would have 0 in the R scale and 470 would be the, anyway, it would freeze salt water at 470 Rankine. Anyways, I've never run into that particular temperature scale too much, and we are not going to talk about it, so that's the much as I'm going to say about it. These are the temperature scales, and the centigrade Kelvin situations here are the ones we're going to work with. And I just want to point out that when you have a situation here, like we just did with the sensible heat transfer, and I have a delta in the T, I can use either one of these. And you will typically find me using the centigrade difference when I'm doing this. But the Kelvin difference is exactly the same, right? Because if I'm taking a difference, all I'm doing is taking 273 plus this one and 273 plus this one and subtracting them, and the 273s go away. So the difference on the centigrade scale is the same as the difference on the Kelvin scale. With a delta, it doesn't matter. You can use centigrade or Kelvin. But if you go to the ideal gas equation of state, which is that's not a delta, and now we have to use the Kelvin. All right, using centigrades in this will cause you to raise your eyebrows, furrow your brow, wring your hands, tear your hair out. You'll say, what have I done? Kelvin only here, right? That will save you a lot of heartache. Okay, so there's that. We did talk a little bit about the absolute zero in the lab, and so I just wanted to give this some context. It's the temperature at which the ideal gas would attain should it exert zero pressure. So in the lab, what we were doing was, if I graphed pressure versus temperature like this, and I take several different values of pressure, temperature for different gases, what I find is that they are fairly linear, but when I trace them all back, I really should dash this so that you don't think that's actual. It goes like this, right? They all go to there, and this is the absolute zero temperature. So with very careful experimental measurements, you can extrapolate these lines when it's an ideal gas all the way back to where they would intersect the t-axis in order for the gas to exert zero pressure. And when it exerts zero pressure, that means it's not moving. Okay. Now, of course, no ideal gas ever does this. It's just an extrapolation to see. But the interesting thing is they all go to the same point, no matter what the gas is, as long as it's ideal. So let's talk a little bit about when a gas is considered to satisfy the model of an ideal gas. Okay. Oops. So when can a gas be modeled as an ideal gas? Okay, and the ideal gas, remember, is a bunch of independent little bouncy spheres bonking into each other, just like a billiards table, right? Just like when you break the pool table, break the rack on the pool table, right? They're just bouncing. They have no idea that anybody else is there, meaning any of the other balls are even there, until they bash into them, right? And at that point, it becomes basically what's called hard sphere scattering, where there's no deformation. It's just bang, off you go. It's just typical mechanical momentum conservation. Okay, so when's a gas ideal? Well, typically you're going to want to talk about a gas that has fairly low density. And while it's got low density, it should be fairly far from the, if you like, the boiling point or the condensation point, right, when it turns into a liquid. So I'll just say far from the boiling point. And this is why air is such a great candidate for it. Air is what, 1 gram per liter or something like that. I don't remember exactly, but it's about a kilogram per cubic meter. So it's got a density which is about 1,000 times less than liquid water. And its boiling point, when does it become a liquid? Right? What's the boiling or the condensation point? What's that temperature? It's here in the centigrade, it's the temperature of what is called liquid nitrogen, because the air is mostly nitrogen. When you condense nitrogen, it's going to do that at around minus 195, minus 200 almost centigrade. So it's far from its boiling point, right? It's been a gas for all that time, okay? So 2 conditions, and you can kind of see low density is useful so that you're not getting the molecules too close to each other, because they do tend to attract a little bit when you get things really close and they can stay there, right? In the case of things like like air in an ideal gas, they're bouncing around so quickly that yes, they are close to each other, but not for very long. They hit and they're gone, right? Higher density would mean you have things forced together and they can stay there and possibly bond. All right, so let's talk a little bit about what happens when the temperature of something increases. We've talked already about how much heat capacity things have and what sensible heats and specific heats are and how to describe them. Let's talk a little bit about what happens to its physical size when temperature changes. All right, so I have for you here a a good old ball on a stick, right? But I've also got a ring on a stick. So as you can see, if I try to pass the ball or pass the ring over the ball, it just barely fits, like so. Now, what I'm going to do, hopefully, is I'm going to heat the ball up. And in doing so, while I am causing the temperature to increase by transferring a large amount of heat to it, I'm causing the atoms in this substance to vibrate much more quickly, right? This is not a latent heat transfer. This is a sensible heat transfer. It's not going to be melting. I mean, I sure hope it's not, because that would be pretty toxic if it did. And I'm going to get the atoms moving a lot faster, and I want to describe what is happening to the atomic spacing when these atoms start moving faster. Okay, so maybe at this point we'll be able to see, if I take the ring, see it's not fitting anymore. I cannot get the ball to fit, the ring to fit over the ball. So what I'll just do here is I'll just hold it for a little while. Ta-da! It's not going through, but it's cooling off, right? It is cooling off. So as I allow it to cool off, you'll see that soon it will go right back through the ring. So in other words, when the temperature is larger, the rule of thumb, with exceptions, the rule of thumb is that substances expand upon increasing temperature. Let's see, almost there. Cooling down, cooling down. How hot is this thing? Oh, wow, it's still pretty toasty. Yeah. Wow, that is very toasty. I'm glad I'm not touching that to my skin right now. I would definitely be burning. I would be burning off layers of skin right now. But yeah, it's close. Anyways, we have that. So, oh, got you this too. Let me show you this one. Come on. There we go. We got this. This is a fun device. I'm going to show you that on this side of the flame. It's just a, doesn't look like much, but when I heat it, fun things happen. And now, oops, you can't see that, sorry. There you go. Now as it cools, as it, see it unwind. No, it's almost back. So this is a really interesting material. It's, well, I don't know if it is anymore, but it used to be a spring-like object inside thermostats. Okay, so if it got too hot or too cold, this spring would change size slightly, and then it would turn on your heater, right? If it got too hot, this thing would expand and it would kind of come like that. And then all of a sudden it would click on the cooler. And then if it cooled off, it would drag this way and it would kick on the heater. So yeah, see, back to normal now, back to straight. This is known as the bimetallic strip. In other words, there's a different metal on the top than there is on the bottom. So, and you can see possibly how thin that is. So getting that to happen, pretty cool little invention. By now? No. Boy, I really heated this thing up, but it's over the diameter, so it should be. Almost, not quite there yet. Incidentally, the opposite to this is how rivets are made, right? So if you want to join two pieces of metal with a rivet, this is basically the idea, except it's not this, it's the other way. Instead of having the ball pass through this initially, I have the ball not pass through the ring. The ring's too small, right? And so then I heat the ring up, the ring expands, I put this in here, the ring contracts, and it cinches. Oh, see, there it goes. And it cinches around the ball like that. And then you can never get them apart without cutting them. Because if you heat it, it's two metals in contact with one another, so they both expand. You can't do anything about it. So let's talk about this. It's known as thermal expansion. This process of things that get larger as the temperature increases. So I thought, well, let's go back to what we think we know about how atoms are bound together, right? If you think about a solid, you might think about something like this, whereby, and this is just a two-dimensional lattice of little balls and springs, right? It's just springs between each one of these. So I just, if I lean on something, it compresses and then I let it go and it springs back, right? Everything does this. I push down on, well, you can't see. All right, so I push on this thing, right? I push on this, and what's happening right now is basically I'm pushing here and the wall's going right? And the atoms are getting a little closer together and they're repelling each other, and I let go and it lets go. Okay, but they're bound, right? So they don't just go flying off, they're bound together. So if I stretch them out, they say, hey, come back, and they come back. So really nice to think of atoms as being bound by springs. What would that mean? The spring model of atoms bound together. Here's the spring model of materials. It would look like this. Here is a graph of a spring potential energy. I'll just call it U spring, right? We know from 4A what a spring potential energy looks like, right? You remember spring potential energy? You had kinetic energy, and then gravitational potential energy, and then possibly you had elastic or spring potential energy, right? So this would be something that looked like a 1/2 times kx squared. Okay, what that means is it's a parabola, right? This thing is a parabola. So it's going to look kind of like this. Okay. If my x-axis, say, right, is down here or something, x, right? So if I go out, it goes up as a parabola. It's a top opening parabola. But what does this mean? This means that as I increase the energy of the spring, right? Perhaps you can imagine if I have a bowl that's shaped like this, and I drop in here a little ball bearing, and I drop the ball bearing from here. Let's assume it's frictionless. Okay, I drop the ball bearing from here. It's going to roll and then roll back, and it's going to always attain the same height because no friction, right? We're not losing anything. If I just set the thing in here, it'll stay right there. If I bring the ball bearing over to here, it's going to roll between here and here. If I roll it between here and here, it'll roll out. So as I give it more energy, it rolls between higher and higher places on the potential energy graph. Okay? What that means is that if I draw these places between here and here, and I give the ball bearing more energy and more energy, what happens to its average position over time? As the ball bearing oscillates back and forth, what is its average position? Now, this is kind of a funny question because the average position it basically spends no time at. But can you see it spends as much time up this slope as it does that slope? So really the average position is still right in the middle, no matter how high up it's oscillating, okay? So this means what I've just showed you with the expansion. So this cannot describe how atoms bond together, because if I heat this thing up by giving it more energy, the spacing doesn't change. But that's not what we're observing. We're observing, for example, that brass ball got bigger, but that's not described by this, so we have to throw this away as a model of material bonding. All right? Okay, so what is going to work? Well, something where as I go up and up and up in energy, the position shifts further and further away. So examine something like this, where I still have the same kind of idea here of something spring-like, right? But as I go further and further out in energy, it goes further and further away. All right, well, let's take a look at this one. I'll draw you something different. Okay, I'm going to draw you this, where I got something like that. How about this as a shape? Okay, now look what happens. Here is the equilibrium. This is the equilibrium spot right here. And it's a little parabola right around there. So that when I take the energy here to here, right? It's the same position as when I take the energy from here to here, right? The energy is bigger or smaller in this range, but the equilibrium position is still the same. So this is the low energy equilibrium position. Notice what happens as I go to larger energies. As I go to a higher energy, maybe I'll go to one up here. And I think about the average position now, I'm going to say it might be more around here. And as I go a little bit further, here to here, definitely different. Maybe about there, right? Same idea. Just imagine this as a shape when I have a ball bearing and it's going back and forth, right? Just like a skater in a half pipe, right? I drop the ball bearing from here, it goes like this, it goes. It's spending more time on this side, which is why the average position is skewed over, right? That means the average position has gone from here to here to here, right? The average position has scooted. It's widened out. Okay, so this is something that is more similar to interatomic bonding than just a standard parabola. It's got to be modified a little bit, okay? However, it does retain the parabola shape down here at low energies, which is really useful. But once you get to higher and higher energies, you notice the position of it shifts over. Okay, so this model at least is going to account for thermal expansion. All right, let's talk a little bit about thermal expansion. I'll draw you what this looks like. It's a percentage. It's a percentage expansion. So if I take this lattice and I say, what would this look like if all of the interatomic distances were increased by 25%? right? It would be some bigger thing, right? Question is, how much bigger would it be? So let's draw, first of all, let's forget 2 dimensions. Let's just look at 1 dimension for a minute. Let's look at what's called a 1D array, or a 1-dimensional lattice, if you like. And I'm going to draw this, say, at T0, okay? Room temperature, right? And I'm going to draw the spacing of these things to be something like this. Okay, a five atom array. Now I'm going to move to temperature T1, which is greater than T0, and I'm going to say the whole thing has expanded by 25%, whatever it is. So let's just say there's a 25% increase. Okay, so now at a 25% increase, what that means is I had 2 spaces, 2 boxes between the atoms here. So that means I have to increase the 2-box space, well, to like 2.5. It's a quarter of 2, right? So we're going to do the first one. I'm going to hold the first one right where it is. Hold the first one right where it is. Okay. And now I've got to increase this by 25%, which means now instead of being here, it's, or is that an increase of 50%? That's an increase of 50%. 25%, I guess, is here. That doesn't seem right, though. Oh, half a box, duh. Oh, man. So my first one, which should have been here, is now there. And the next one, which should have been 2 boxes away, is now 2.25 boxes away, which is here. And my third one, which should be 2 boxes away from this one, is now 2.25 boxes away, which is over here, or 2.5, like so. No, it's 2.5. It's got to be, yeah, that's right. Yep. And so the last one here is now 2 boxes away from that, which it's now here. Okay, so everything is expanded by 25%, but look at what that means for each of the distances as to where it used to be, right? So this one's going to stay the same. Now this one moved a little bit. This one moved quite a bit more. This one moved quite a bit more, and that one's moving quite a lot more, right? So it's like it's compounding, right? It's compounding. So can you see that how much it expands depends on how much size it had to start with, right? If I had drawn like 12 or 14 or 15 of these things out here, by the time I had drawn the 12 to 15, the expansion would be really large, right? I only drew 5 and I'm already, it's already off by a full lattice spacing from up here. It's 2 boxes off from what it used to be, right? If I had drawn 5 more, then it would have been the 4 boxes off, right? Et cetera, et cetera. So the amount of expansion that it feels, I'm going to call this L0. That's its original length. Its new length is this L plus delta L. Oops, L0 plus delta L, like so. Where delta L is now this thing. And how much that delta L is depends on what L0 was. So what should delta L depend on? Okay, well, suppose I hadn't heated it up quite so much. Well, I wouldn't have gotten the 25% expansion then. Or you could go the alternate way and say, what if I heated it up way more? Well, then maybe the expansion would have been 50% instead of 25. So the first thing delta L depends on is, what's the change in the temperature? How much do you increase the temperature? right? We've already talked about the fact that it depends on what the original size of the material was. Right, L naught. This is delta T. And it turns out that different materials expand at different rates. So there's a material dependent, say, coefficient in here. It depends on what the material is. We'll just call it alpha. In other words, brass, right? Brass expands at a different rate than iron. And iron expands at a different rate than copper, than aluminum, whatever have you, okay? So with all of this together, we can arrive at a pretty interesting description mathematically of what's going on with thermal expansion. And we can also expand it to further dimensions. So using this in one dimension, I could certainly do the same thing in 2 dimensions or in 3 dimensions, and I could get an area expansion or a volume expansion, okay? But nonetheless, we'll just stick with 1D for today. Maybe we'll come back to 2D tomorrow. So the amount depends on its original size, the material, and the temperature change. So hey, just multiply all 3 of those together. It'll be easy. It'll be alpha times L naught times delta T. And I'll get units of distance as long as the dimensions of alpha are 1 over centigrades, right? Because this is a delta, so I can use centigrades, and that's what I'm going to do. Or if you want to use Kelvins, fine, that too. But as long as alpha is in 1 per centigrades, then I'll get a length unit here because of the length unit here, all right? So just by way of about how big is this alpha for materials. So I had a couple of, let's see here, I had a table of a couple of these things here. They're usually in the 10 to the minus 6 or 10 to the minus 5 range for things like metals. Okay, oops, alpha. Alpha is around 10 to the minus 5 to 10 to the minus 6 per centigrade. So that's giving you an amount of how much expansion you should expect per centigrade, right? So a 25% increase would be quite a bit. Now, this is a fairly well-known phenomenon, okay? And you can see engineering taking into account the fact that things heat up and cool off during even the day-night cycle. So, for example, take something that's really large. You're gonna have to compensate or allow for expansion of that material during times when it's getting beaten down by sunlight, right? And then during the nighttime, it's gonna go back to a smaller set of dimensions. One notable thing for me to think about here is the Golden Gate Bridge. The Golden Gate Bridge is really long, and it's made of things like metal. And it expands because there is actually sunlight in San Francisco every now and again, but mostly it's just always cold, so they didn't really worry about it. No, that's not true. But on a hot day, the Golden Gate Bridge can expand up to 1 meter. So you can't just take the bridge and go, it's between here and here, build it like that, and then firm the ends up, because once it starts heating up, it's going to buckle. Right? It's going to be trying to expand, and it's going to go like this. So on bridges, you'll see them. They build in these joints that look like this, called finger joints. They're literally called finger joints. And you drive over them, and you go bum bum, right? And what happens is, as the temperature increases, these things just go, and it decreases, right? And it shrinks back. It goes like this. So literally, the bridge has to have a little bit of ability to rock, to move, in order to have an expansion. It's really takes a little bit of engineering to figure out how to do this, right? So very, very large bridges, you have to allow for this heating and cooling. Um, and you see it in a lot of other places as well, right? Where things need room to expand when the sun heats them up. Um, all right. You know what? I think we are just about out of time today. I'll start tomorrow here by thinking about the following situation. I want to think about this exact situation. We're going to do an example calculation with this, and I'll start tomorrow with it. But the idea being that suppose instead of, these are both brass, which you probably can't notice, but that's okay, I'm telling you. Suppose that I had a brass, let's say I had one of these brass ring and a steel ball, okay? And I want to heat them both up such that I can get this to happen. Now, and I want to find out how hot I have to heat these things up. So it's going to depend, because now I've got this, I've got the brass ring, so I've got this coefficient, and then I've got the steel ball, so I've got that coefficient, and I'm going to have them expanding different rates as I heat them, but I want to expand them to the point where they both reach a common size, and we can get this to happen. So I thought that'd be a fun problem to start with. So we'll do that. Looks like we'll start off with that tomorrow, and that will be Thursday. Yeah, tomorrow is Thursday. So let's do that tomorrow, and we'll go from there. I think what I would also like to do is, I think I'd also like to give you a concept quiz. So I think I'm going to do that tomorrow also. Where it's kind of like a PLC question. We've had one already, but it's kind of like a conceptual question I want you to try and answer, all right, without doing a lot of calculations. So I'll put that up for tomorrow, and you can have a go at it, and that'll help us keep first law conceptual reasoning in tow with us. How about that? So look for that tomorrow, and we'll go from there. All right. I'll post something about that. Maybe I'll post an announcement about that. All right. Great. So happy rest of your day, folks. It is supposed to be slightly cooler today than it was yesterday, and the spring season starts Friday, Saturday, and that's about when the heat wave that we're in is supposed to be easing off. So keep your eye on the prize, and we'll see you soon. All right. Happy rest of your day.